Now that we have seen how the random forest algorithm works, we will present a clever and statistically efficient way to compute the prediction error of a random forest, the out-of-bag error. This error is computed without having to divide the dataset into a training sample and a test sample. The calculation of the out-of-bag error is based on the following observation. Each observation is only used by a part of the trees of the forest and can thus serve as test points for all the other trees. Let's try to summarize the procedure in a concise way. Let's imagine that we have already trained a forest on the dataset Dn, and we now seek to calculate its error via the out-of-bag procedure. For each observation of the dataset, we will apply the following procedure. Let's take the ith observation. Consider all bootstrap samples that do not contain this observation. The corresponding trees have not been trained using the ith observation. We can then compute their prediction in this observation and aggregate the predictions of these trees to obtain the prediction of a subforest composed of the trees that have not been trained with observation I. We can then calculate the error of this subforest in observation I. Therefore, for each observation, we can easily calculate the error of a subforest composed of trees not using this observation in their construction. The errors thus obtained can be averaged to obtain the out-of-bag error. This procedure does not require to divide the dataset into a train and test sample. Each data is used by a part of the trees and is therefore involved in the construction of the forest. The out-of-bag procedure uses the fact that each observation is not involved in the construction of all the trees of the forest and can thus be considered as a test observation for the trees that did not use it. Moreover, this method is easily parallelizable. The error is calculated for each observation separately. Besides, when the number of trees tends to infinity, the out-of-bag error is equivalent to the forest error calculated on the test set. Indeed, notice that the out-of-bag error does not correspond to the forest error. It corresponds to the error in prediction of a subset of trees of the forest, this subset depending on the observation in which the error is calculated. This is a drawback of the method. If the number of trees is too small, the out-of-bag procedure does not allow for an accurate estimation of the forest error on a test set. Here is how the out-of-bag procedure works in pictures. Let us imagine that a forest has already been trained on the dataset Dn. Here is a diagram of such a forest. Now, consider the first observation of the dataset Dn. Consider the bootstrap samples of the forest not containing this observation, for example the first bootstrap sample, some others, and the last one. For all corresponding trees, we will compute the prediction in the first observation x1 of the dataset. We will then aggregate these predictions by mean or majority vote and obtain the out-of-bag prediction of the forest for point x1. Since we also have access to the true label y1 of the observation, we can calculate the loss associated with the out-of-bag prediction for the first observation. Everything we did for the first observation, we repeat for the second observation x2. In this way, we consider all bootstrap samples not containing x2. For all corresponding trees, we will compute the prediction of these trees in x2. We then aggregate these predictions by mean or majority vote to obtain the out-of-bag prediction of the forest for point x2. We can then calculate the out-of-bag error for the second observation. We can repeat this procedure for each observation and thus obtain n errors. These errors can then be averaged to obtain the out-of-bag error. All the steps in the procedure for calculating the out-of-bag error are described precisely on this slide. It is nothing more than the mathematical formulation of the previous slide.